Okay, so just a few more notes on applying Gauss's law to spherical charge distributions. We're only going to do part D and E for this problem, but what you notice about this problem is rho, or the volume charge density, is not uniform. They give you a function for rho, okay? And just as the picture suggests, it looks like the density of the charge is really heavy in the middle, and then the density is less as you go further out from the center of the sphere. Okay, so we need to figure out how to deal with problems like this. Okay, so we're only going to deal with part D and part E, figuring out rho naught from that equation, and then finding the electric field of that non-uniform charge distribution when R is less than big R. Okay, so since rho is not uniform, if you want to figure out, okay, let's just say we have a Gaussian surface in here. Okay, if you want to figure out, and it has radius little r, and if you want to figure out the electric field, or if you want to figure out how much charge is enclosed, you cannot just use, so before we have just been using Q enclosed equals rho times the volume. You can't actually do that anymore. You actually have to use an integral. Okay, so if you want to figure out Q enclosed, so this only works for uniform rho. For non-uniform, we have to use, to figure out charge, Q is equal to integral rho dV. Okay, so dV, that's suggests to do a volume integral, which is a triple integral. Okay, all of the AP problems that deal with non-uniform charge distributions, they will always make rho as a function of r. If they made it as a function of r, theta, and phi, that's when you would have to do a triple integral, but they don't. I've never seen a problem where they do that. Okay, so here's the trick for dV then, since rho is a function of r. Okay, and I actually did not come up with this. This is a student's idea, which is awesome. So, so what does dV equal? dV, as long as it's a function of, as long as rho is a function of r, dV, we can rewrite it just as 4 pi r squared dr. So then, typically for us, any problems that we do, Q enclosed will be integral of rho times 4 pi r squared dr. So how do I remember that? Okay, well, it kind of looks like area times radius, which would give us volume. But the best way to remember it is to just remember what the volume of a sphere is. So the volume of a sphere is 4/3 pi r cubed, okay, which means, so here's the trick that the student noticed. If you take the derivative of volume with respect to r, what do you get? You get 4/3 pi r squared times 3 if you do that derivative. Okay, and that 3 cancels that 3, and so you get 4 pi r squared, which means that dV, if I multiply the dr over, is 4 pi r squared dr. Okay, so that again is a student's trick, not mine. But easy way to remember. Just remember volume of a sphere. Okay, and then if you have to do this integral, I guess remember this integral rho dV, but then just remember to get dV, you just take the derivative of that volume with respect to r, and you get that. Okay, so we have to use that for this for these types of cases, which are not as common, but it does happen. 2018's free response question has this problem on there. So, okay, so we're just going to do part D and part E. So part D says derive an expression for rho naught. Okay, and so here's what we know about this problem. We know the total charge is Q. Okay, and we have rho as a function of R. Okay, so what that means then is that applying this integral, that means that Q, the total charge, is an integral of rho of r dv, which is equal to integral, what is rho? Rho is equal to rho naught times 1 minus r over r. Rho naught times 1 minus r over r. Times dv, we said we can write that as 4 pi r squared dr. Okay. The only thing we need to figure out is our limits of integration. Okay, so we want to make our limits for, so the limits of integration will be dependent on how much radius we actually want to have. Since we're talking about the total sphere, okay, we want to have the radius be all the way out to here, so radius of big R. Okay, so our limits will go from 0 out to big R. So rho naught, I'm not going to rewrite that actually. Let's just write our limits up here. So from 0 to big R. Okay, and so now we just have to do this integral. So let's pull constants out. We have 4 pi, rho naught is a constant, and we're left with integral 0 to r, distributing that r squared. I guess I'll do that here in a second. We have r squared times 1 minus r over r dr. Okay, so let's do that integral. You would get 4 pi rho naught, or let's distribute the r squared first. So 0 to r, we would have r squared minus r cubed over big R dr. And now we can do that integral. So 4 pi rho naught times 1/3 r cubed minus 1/4 r to the 4 over big R. And we're evaluating that from 0 to big R. And so we would get 4 pi rho naught times 1/3 big R cubed minus 1/4 big R to the 4 over big R. Okay, and then we would get minus 0 plus 0, so we're not even going to worry about the bottom limit. All right, and one of those, so this r cancels out one of those, and we have a 1/3 r cubed minus a 1/4 r cubed. If you find common denominators, I think you get 1/12. Okay, so what we end up having is q is equal to 4 pi rho naught times 1 over 12 big R cubed. Okay, and we can simplify that a little bit more. So 4 over 12, if you divide top and bottom by 4, you get 1/3. Okay, so this is going to equal, let's see, we would have a rho naught pi r cubed over 3, it looks like. Okay, and all of that equals q. Again, what are we solving for? We're trying to figure out what rho naught is, and so now we can solve for it. So rho naught equals 3q divided by pi big R cubed, it looks like. And so that's rho naught. Okay, part D, we want to determine the magnitude of the electric field as a function of r for r less than or equal to r. Okay, so applying Gauss's law, again, we only want, let's see, we only want this amount of charge within our Gaussian surface. Okay, so applying Gauss's law, using that Gaussian sphere, we would have, what part is this? This is part E. Okay, so part E, we have closed integral E dot dA equals q enclosed divide epsilon naught. Okay, left side of the equation is easy. We'll just do that first. It always turns into E times area of the Gaussian sphere, or E times 4 pi little r squared. Okay, the right side, Q enclosed, we have to use the volume integral again. So Q enclosed equals integral of rho dV, which is equal to integral of rho naught, well, it was rho naught 1 minus r over r, but we know rho naught now. Rho naught is 3q over pi r cubed. I'll just write it out. So we have rho naught 1 minus r over big R. dV is 4 pi r squared dr. Okay, and then plugging in rho naught, we have 3q over pi r cubed. 3q over pi r cubed times 1 minus r over big R, 4 pi r squared dr. Let's pull out some constants so that we have Q enclosed is equal to 3q over pi r cubed times, it looks like 4 pi, integral of 1 minus r over big R, r squared dr. What are our limits? So we're going to add, so for our integral, our limits will be from 0 out to our Gaussian surface. That's the amount of charge that we actually want to count. So out to little r. Okay. So from here, same. So this integral looks like the one we just did a minute ago. I'm going to ignore this stuff for a minute. Okay, let's just worry about this integral. Okay, I'm going to distribute that r squared so that we have 0 to r, r squared minus r cubed over big R dr. Oh, yeah, dr. Okay, and then that integral becomes 1/3 r cubed minus 1/4 r to the 4 over big R. And then we want to evaluate this from 0 to r. Okay, and if we do that, we get a 1/3 r cubed minus a 1/4 r to the 4 over big R minus 0, minus 0. So the 0 limit cancels out. Okay, all of this times this stuff. Okay, really quick, let's simplify this. So the pi cancels the pi, and we have 4 times 3 is 12. So we're going to have a 12q over big R cubed. It looks like. Okay. Can we simplify this anymore? Should we? I guess we could distribute that 12 if we want. We could factor out some r's. I don't know. I guess let's just leave that the way it is. Okay, so this is, again, this is Q enclosed equals all of that stuff. I guess I'll distribute the 12. So we would have Q over R cubed times 4R cubed minus 3R to the 4 over big R. Okay, and I'll just leave it like that. So setting the left side of Gauss's law equal to the right side, we have E 4 pi R squared equals Q enclosed, so Q times 4R cubed minus 3R to the 4 over R divided by epsilon naught. So we have that, still have that R cubed epsilon naught. Okay, if I divide both sides by R squared, I have E equals Q times 4R cubed minus 3R to the 4 over big R divided by 4 pi R squared R cubed epsilon naught. And we could simplify this. We could distribute that 1 over R squared throughout everything. Kind of clean it up a little bit if we want to. So E is equal to Q times, I'm distributing 1 over R squared, this 1 over R squared throughout everything. So we would have Q times 4R minus 3 r squared over big R divide 4 pi r cubed epsilon naught. I'm just going to leave it like that.